Welcome back to the deep dive. If you follow machine learning at all, you are constantly bombarded with news about the model that just hit the top of the leaderboard.
It's always a race for that top score, that 99%.
But here's the crucial industry secret, and it's all over the sources you shared with us. The models that win the awards often aren't the ones that actually win in production.
That's a fundamental distinction. In the research phase, the only mandate is to maximize performance.
Right.
And that inevitably leads to building models that are larger, deeper, and more complex. That complexity is what gets you those tiny marginal accuracy gains.
Okay, so we have our perfectly trained, massive model. We've hit peak accuracy. But that 99% score doesn't just automatically translate into something, useful in the real world.
It really doesn't.
So our mission for this deep dive is to figure out what happens after the model leaves the lab. What are the engineering secrets, the optimization, the inference techniques used to take that massive model and turn it into something fast, scalable, and cost-effective enough for real users?
Exactly. The whole game changes at the deployment stage.
The metrics are different.
Completely. We go from a purely academic focus to an operational one. Suddenly, 4 new constraints just dominate everything. Runtime, resource utilization, cost, and most importantly, the user experience.
So a model can be 99% accurate, but if it takes too long to respond or costs a fortune to run, it's a failure.
It fails in the market, absolutely.
The sources gave us a perfect comparison for this idea of Model A versus Model B.
Right. Model A is your lab champion. It's got that stunning 99% accuracy, but it's got a 2-second runtime, which is a lot of latency for a user, and it's about 125 megabytes in size.
And then there's Model B.
Model B is a little less accurate, say 97%, but its runtime is a lightning-fast 0.1 seconds.
Wow.
And it's tiny, only 10 megabytes.
So in academia, Model A is the clear winner. But in the real world, you're almost always going to choose Model B. Why?
Because user experience just crushes marginal accuracy gains. I mean, in a modern app, a 2-second wait time is an eternity.
People will just leave.
They'll abandon it. Model B is responsive, it's easy to scale, it's way cheaper to run. If the user gets a good enough answer, instantly they're happy. That 2% accuracy drop is a tiny price to pay for a massive gain in satisfaction.
So the goal becomes getting the intelligence of Model A into the efficient body of Model B.
And that is the entire field of model compression. It's a set of techniques designed to shrink the model and its computational cost while trying to hang on to as much of that performance as possible.
This is the critical pivot.
It is. Model compression lets us take a complex model, slim it down, lower its memory footprint, and make it practical to run. And the 4 techniques we're about to talk about are foundational to pretty much everything in AI today.
Okay, let's start with the one that sounds the most esoteric, but it's actually pretty brilliant. Knowledge distillation. How do you distill knowledge from one model to another?
The core idea is you train a small student model to mimic a much larger teacher model.
So the teacher is the big, complex one.
Right. It's highly accurate. The student is much smaller, simpler, and faster. It learns not just from the raw data, but from the teacher's nuanced predictions.
Okay, so the teacher trains on a huge data set and learns all the patterns. That's the knowledge. But what exactly is the student mimicking? It can't just be the final answer.
And that's the genius part. It doesn't just mimic the hard prediction, like dog. It mimics the teacher's internal confidence, the soft targets.
What do you mean by soft targets?
So the teacher might be 90% sure it's a dog, but also 8% sure it's a fox and 2% sure it's a wolf. The student is trained to replicate those subtle probabilities.
Ah, so it's learning the teacher's uncertainty in its reasoning.
Exactly. It transfers that nuanced understanding, which makes the smaller student model way smarter than if it had just trained on the raw data by itself.
Which is why the classic example, Distilbert, is so powerful.
Absolutely. Distilbert is the student of the original BERT model. It's about 40% smaller.
And the performance?
It keeps around 97% of BERT's language understanding capabilities. But here's the kicker. It's roughly 60% faster at inference.
So it is Model B, built from Model A's knowledge.
That's the perfect way to put it.
But that 3% drop in accuracy, where does that actually show up in the real world? Are there cases where you just can't afford that drop?
That's a great question, and it's what deployment engineers wrestle with every day. That 3% difference usually appears in, edge cases, really ambiguous inputs, or highly nuanced situations.
So for something like general sentiment analysis, it's probably fine.
Oh, for sure. The 60% speed gain is way more valuable than a rare error on a tricky phrase. But if you're classifying rare diseases or analyzing complex legal text,
Then you need that 99%. The cost of an error is just too high.
exactly, it's always a calculation of utility versus risk.
Fascinating. Okay, let's move on. Our second technique, pruning, feels less like teaching and more like surgery.
Pruning is simplification by elimination. It's based on a simple idea. Not all parts of a model contribute equally.
So you just find the parts that aren't pulling their weight and remove them.
Right. If you think of a simple decision tree, the goal is to chop off branches that don't add much value, but add a lot of complexity.
And you want to get the biggest reduction in complexity, the most nodes removed, for the smallest hit to your accuracy.
Precisely. We do the same thing with neural networks. We look for weights and neurons that are basically just redundant baggage. And we generally split this into two types: neuron pruning and weight pruning.
Let's start with neuron pruning.
Neuron pruning is more aggressive. You're deleting entire nodes from a layer.
So you're actually changing the model's architecture.
You are. The weight matrices between layers literally get smaller. The benefit is immediate: less calculation, so you get faster inference and lower memory use. The whole structure shrinks.
And weight pruning is different.
It's more fine-grained. You aren't removing the whole neuron, just individual connections between them. You do this by setting their specific weights in the matrix to 0.
So the matrix itself doesn't get smaller dimension-wise, but it becomes sparse.
Exactly. You get a sparse matrix, which is just a matrix that's mostly filled with zeros. Storing that is much more memory efficient. And more importantly, modern hardware is really, really good at skipping calculations that involve 0, so you still get a speed up.
So our third technique, low-rank factorization, takes us into the math. We're attacking the weight matrices themselves.
This is a really powerful one. The core idea is that you can take a big, complex weight matrix and approximate it by multiplying 2 or more smaller, lower-dimensional matrices.
We hear the term rank a lot here. What does the rank of a matrix really mean in this context?
A simple way to think about rank is as the number of core ideas or independent features the matrix has learned. A high-rank matrix is often redundant. It's full of information that could be expressed more simply.
So low rank means you found the most essential information.
Yes, like summarizing a 500-page book with its 10 most important points. Those 10 points are the low-rank approximation of the whole text.
And that's where mathematical tools like SVD, singular value decomposition, come in.
Right. Techniques like SVD are designed to find those core components. They let us break down the original huge matrix, and then we choose a new, smaller rank, which we call K.
And choosing K must be the ultimate trade-off dial.
It absolutely is. A smaller K means a much smaller model and faster calculations, but you lose more of the original information. Once you pick K, you use the new, smaller factor matrices for inference. The computation just becomes dramatically less complex.
Which brings us to our last general technique. Quantization. This isn't about structure or math, it's about the numbers themselves.
Correct. By default, models are trained using 32-bit floating point numbers. They're super precise, which is great for training. But when your model has billions of parameters,
That's a ton of memory.
an enormous amount, quantization is the solution. We just use a lower bit representation.
So instead of 32-bit, you use 16-bit, 8-bit, even 4-bit numbers.
Exactly. And the savings are direct. Going from 32-bit to 8-bit, for example, cuts your memory footprint by about 75%.
75%. That's a massive saving. But what's the cost? We're trading raw precision here.
The predictions become more approximate. Let's say you have an image classifier on a mobile phone where memory is tight. The 32-bit model might be able to tell you it's a northern cardinal. The 8-bit quantized model might just say a bird.
So you lose the fine-grained detail.
You do. But for many mobile apps, just knowing it's a bird is perfectly good enough. Quantization is a necessary and incredibly effective tool in those cases.
So we've covered the 4 pillars: distillation, pruning, factorization, and quantization. But when we start talking about large language models, the whole game changes again.
It really does. We're not just processing a fixed input anymore. We're dealing with autoregressive decoding, generating text token by token.
And that creates huge challenges for memory and scheduling.
It does. Every new token needs the key and value vectors, the KV cache of all the previous tokens. That cache grows and grows, and the fact that outputs have variable length just wreaks havoc on traditional batching.
Which sets the stage for these newer, more specialized techniques. Let's start with continuous batching. Why did the old way of batching fail for LLMs?
Traditional batching just wasn't built for it. You'd batch, say, 5 requests. One asks for a sentence, another asks for an essay. The GPU would finish the short request and then just sit there idle, waiting for the longest one to finish. It's incredibly inefficient.
So continuous batching keeps the GPU busy.
Constantly. The system monitors every sequence. The moment a request is done, it hits that end of sequence token. It's immediately swapped out for a new one from the queue. It maximizes GPU utilization. No wasted time.
Next up is pre-fill decode disaggregation. This suggests LLM inference isn't one process, but two.
It is 2 stages with totally different needs. Stage 1 is the pre-fill. That's when the model processes the user's prompt. It's very compute heavy.
At stage 2.
That's the decode stage, generating the output 1 token at a time. This is memory bound and extremely latency sensitive.
And if you run both on the same hardware, the big pre-fill jobs will constantly slow down the urgent decode jobs.
That's the conflict. Disaggregation solves it with dedicated GPU pools. One pool for the compute-heavy prefill, another for the latency-sensitive decode. They stop interfering with each other.
Now for the big memory problem. KV caching and this brilliant idea of prefix-aware routing. So the KV cache is necessary, but it grows and eats up all the memory.
It's the biggest constraint. But we noticed that in production, a lot of queries share the same beginning.
Like a system prompt.
A system prompt, a common question, a long chat history. The KV cache for that shared prefix can be reused. You don't need to recompute it.
And that's where prefix-aware routing becomes critical for scaling this up. You don't want every GPU to be recalculating the same prompt cache over and over.
Right. The router is like the system's brain. It keeps a map of which GPU replicas have which KV prefix is already cached. A new query comes in, the writer checks its prefix and sends it to a GPU that already has that cache ready to go.
So you avoid all that redundant work. That's a huge saving at scale.
A massive saving in both time and compute.
Finally, let's touch on model sharding, specifically for the mixture of experts, or MOE architecture. Why do they need a different strategy?
MOE models are structured differently. They're not one big, dense network. They have many smaller expert networks. For any given input, only a few of those experts are actually used.
So splitting the whole model up like you normally would is inefficient.
Very inefficient. Instead, they use something called expert parallelism. You split the different experts across different GPUs.
So each GPU only holds a fraction of the expert.
Exactly. This lets you scale the number of parameters into the trillions because you don't need to load every parameter onto every single device. The attention layers, though, those have to be replicated everywhere to coordinate everything.
This has been a true deep dive. We've gone from the tension between accuracy and speed to the mechanics of shrinking a model, and ended with these specialized techniques for making massive LLMs actually work in the real world.
I think the sources really highlight that the future of AI is built on this invisible, relentless optimization. Every single choice, from the rank K you pick to the bitwidth for quantization, is a calculated trade-off.
And it brings us right back to that first question. If Model B is 60% faster but 3% less accurate, and that creates a better user experience for millions, what does perfect accuracy even mean in the real world?
Well, we make that same compromise all the time in our daily lives, don't we? We prioritize speed over perfection.
How so?
We use navigation apps that are maybe 98% accurate because waiting an extra 5 minutes for one that's 99.9% accurate just isn't worth our time. The utility isn't there.
It seems that in practical AI, the highest utility comes from the fastest model that is good enough and scalable. It's a compelling thought to consider how often these silent, invisible engineering secrets are shaping the AI services we use every single day.